We're on page 25. Our quick look at the calendar tells us that we are today talking about graphs of polynomial functions. So we'll look at that today. You can see the word polynomial appearing over the next several classes. So we're going to keep with this idea as we talk about polynomials and lots of stuff related. Our next quiz is on the 13th. What day is that? Friday? Yes? All right, our quiz is on Friday. One note, Monday, a week from today, there are no day classes. What's going on Monday? I wanted to say it was Patriots Day, but I don't know. Yeah, could be. Yeah. Okay, so no day classes this coming Monday. All right. So here we are, page 25. We'll go up to the middle and start with number 1. Eric?
Polynomial functions.
Okay, so now we're going to fill in and we're going to generalize this idea of constant function or linear or quadratic and all that. Here's the form for a polynomial function. You have some power on the x, let's just call it x to the n for some generic power, plus then you have the next smaller power, x to the n minus 1, plus dot dot dot, and eventually you get down to things that look more familiar like an x squared and an x and then some constant term. And we actually have to give names to these constant terms. Now you guys know ax squared plus bx plus c is like your standard quadratic looking thing. But we're not going to, and like mx plus b is the standard what? The slope intercept, it's a standard form for a line. But the difficulty is that we can't just use a, b, and c as we go to these higher powers because I might run out of letters. If the power up here is 30, well, I don't have enough letters in the English alphabet to use A, B, C, D down to Z, right? So we do something more general. What we're going to do is we're going to say that this guy right here is A sub 1. The subscript is just our way of numbering. It's just that A sub 1 is just some constant. And this guy in front here is A sub 2, which means here at the end, what should it be? N minus 1. So I think Sam has found the power, the pattern, that whatever the power is, that's just the little number we're going to put at the bottom. So who's the first guy? A sub n. And I left a little blank at the end. If we follow the pattern to the right, A sub 0. So that's our general polynomial function of degree n. So don't get lost in all the symbols and everything. I'd like you to be comfortable with looking at something like that. That right there is a polynomial. You can see the coefficients. You've got 2 and -3 and -7 and 5. Those are just the things we're calling the A1, A2, and A3 up above. So what we're going to do is we're going to identify a lot of stuff about that polynomial function. So right here is all the vocabulary we're interested in: degree, leading coefficient, leading term, constant term, and the coefficients. I don't know what happened with my formatting. Somehow I missed this, but that number 3 should have been several lines below with some blank space for you. Apologies. So let's go ahead and see if we can squeeze in some of this information. The degree is the highest power you see. What is the highest power? 4. The degree in this case is 4. We care about the degree because knowing the degree gives you a lot of easy information about the graph. The graph of this 2x to the 4th minus all that stuff, it's a complicated thing. It's got some ups and downs, but there's going to be some information for us to grab very easily just looking at the 4. Next thing is the leading coefficient. That's the number sitting in front of the highest x power, and that's a 2. Leading coefficient is 2 in this case. The leading term is the 2 together with the x's. 2x to the 4th is the leading term. Any questions on the vocabulary so far? The constant term is the term without any x's. It's 5 in this case. And then the coefficients are just the numbers in front of the x's. We've already seen the first number is a 2. I'll put a comma because I'm going to list them. What's the next coefficient? It's -3. I like that Sarah has grabbed the negative in front of that. That's part of the coefficient. And then a -7. And then finally, +5. It is, even though it's by itself. So maybe my definition where I said coefficients are the things touching the x's, it's great, except when we get to the end. 5 is still a coefficient. Good question. Any other questions about the vocabulary? Okay, let's go to number 5. Iris, sorry, number 3. We're on page. Go into 3, which starts there, all.
Polynomial graphs that are smooth curves. Does not have sharp curves. There are 3 examples.
Okay, so let's take a look at these 3 graphs. These are graphs of 3 polynomial functions. It's true. Domain is definitely infinite, left and right. I want to highlight the words that Iris just read. She said smooth and continuous. Can you guys with your hands show me the graph of y equals absolute value of x? What does that graph look like? Use your hands, use your arms. Yeah, so it's just a V, right? Is that smooth with no corners? No, there's a real sharp corner down there at the origin, right? That's something that is not smooth. It's something where the rules change quite drastically at that one instant, at the origin. Do you see any corners in these pictures? No, and this is characteristic of every polynomial. They have no corners. They are very smooth. Every kind of change, like I would say there's a change happening down here, but it's a very gradual change. It's a gentle change, as opposed to the absolute value, which is a very harsh change at that one moment. And the other word that Iris said that I want to talk about is continuous. No gaps, no holes. Do you guys remember this function? We called it the floor function, or a step function, look like a staircase. Are there gaps in that function? Plenty of them. Are there holes in that function? You bet. Are there any gaps or holes in these 3 pictures? No. And this gets to what Iris had said before. No, the domain is infinite, meaning you can draw the picture left and right forever, no problems, no gaps, no holes. Joe? Correct. Polynomial functions just have one smooth, continuous graph that you can draw in one piece without picking up your pencil. Matt?
Could there be any flat areas?
Flat. So I would say that that at this point right here, the graph is flat for just a moment. If you're asking me if a polynomial can look like that for a while, the answer is no. Yeah, polynomials are either going down or going up, or for just a single moment they are paused, but it's so quick that it's, you know, like if you were watching a ball go up and down, like you would not even see it paused at that moment. It would just, yeah, good questions. Okay, let's go back to Matt for 4. Okay, so I've got 3 equations here. Let's first take a look at the degree. What is the degree of this first one on the left? Degree is 4. Degree, remember, is the highest power you see. Can you guys fill in the degrees of the other 2? Okay, what's the degree for the middle one? 3, and for the last one, 5. Is the degree always the first term you see? No, they were for these, and usually if it's in standard form, it'll look like these, but if the end of this here had a plus x to the 7th, what's the degree? It's 7. Don't trust that I'm going to put the degree nice and easy for you in the beginning, right? You just have to find the highest power. Okay, next thing we're going to fill out is number of TP, turning points. So right down here at the bottom is a turning point. And then up here at the top is another turning point. And then finally, one more turning point there. So how many turning points does this one have? It has 3. Count turning points for the rest. Michael. Michael is jumping ahead, but yes. Okay, how many turning points for the middle one? 2 for the last one. 4. Okay, Michael, what did you say? Michael says the number of turning points is always 1 less than the degree. Does this evidence suggest that he's right? That the number of turning points is always 1 less than the degree. Good observation. We'll write that down on the next page. Next one, number of extrema. Extrema. Is that what I meant to say? That is not what I meant to say. Because extrema, I think I'm calling a synonym for what? Turning point. Like I'm saying, like if I say an extreme value, I'm talking about a max or a min, which is the same as the turning points. Cross that off. X-intercepts is what I want you to count. Number of x-intercepts. Okay, for the first one, how many x-intercepts? 4. Somebody else in the middle? How many x-intercepts? 3 there. And 5 over here. We see a different pattern related to the degree. What can you say about the number of x-intercepts? Sure looks like it's the same as the degree, right? Whatever the power is, that's how many x-intercepts you have. In fact, I think we've mentioned this a couple of times informally in this class, something called the fundamental theorem of algebra, which says whatever the degree is, that's how many solutions the equation has. Whatever the degree is, that's how many solutions the equation has. So if I asked you to solve this equation right here equals 0, I don't know how we're going to do it, but I can tell you there's going to be 5 answers because that's the same as the degree, and every one of those answers is going to turn out to be an x-intercept. We'll see that. So this is kind of coming attractions here. Is there a question, Matt?
It looks like on the last equation, the value was always.
Okay, so Matt is trying to contradict me, which I don't appreciate. No, I'm kidding. Matt is thinking, which I do appreciate. Matt says if it's minus 20, what would that do to the graph? It used to be minus 7. If I make it minus 20, can you be very specific and tell me what is going to happen to the picture? It's going to shift down. In fact, you could tell me exactly how much it's going to shift down. How much will it shift down? Like 13, right? If it went from 7 to 20, 12.8. So Matt says if we take this graph and we shift it down 12.8, let's see. So I feel like this x-intercept is going to go away, but maybe we'll get another one coming in there, right? So we'll just move that x-intercept. And I feel like this one's going to go down, but then maybe we'll get a different one over here. So that would change. And what else are we saying? Like maybe this guy will lose, but we'll get one here. So what are you talking about? I feel like, I mean, they're going to move. Matt is saying we're going to lose some.
The one above.
So this one right here will lose. It's not going to get replaced by somebody else. You guys see it's not, right? There's nothing up there like this. This is going to miss. Everything is going to go down. So is it true that the number of x-intercepts is always equal to the degree? No. That's given us a good example where it's not true. So we're going to say something that is true on the next page. But Joe, can you grab the thinker and we'll pass it up here? Well done, Matt. Let's go to the next page. Number 5 is some vocabulary. Hazen. Okay, number 6, Megan. Okay, so what did we decide? Yeah, it's n minus 1. This was what Michael had observed, was that whatever the degree, it sure looked like there was one less turning point, one fewer turning point. Okay, now I said at most, because it doesn't have to be, and this is kind of what Matt was talking about. For example, y equals x to the 4th. How many turning points would you expect? Remember, it's one less than that number, so 3 turning points. But if you graph y equals x to the 4th, it's going to look an awful lot like y equals x squared. How many turning points does it have? Just the 1. Well, that's okay. If I were to give you more stuff here, you know, plus 3x to the 3rd minus 7x squared, now probably it has 3 different turning points. So that phrase at most is important. We'll go to 7 for Sam. Okay, let's fill in this one. How many x-intercepts did we see? It felt like it was n. This key phrase at most is what Matt pointed out to us. Doesn't have to cross n times, but it could be up to that many times. Could also be less. For example, y equals x squared. Can you guys show me with your hands? What does y equals x squared look like? So we've got this curvy looking thing. How many x-intercepts does it have? It has just the 1. How many x-intercepts were we expecting? 2. X-intercepts and the degree, a lot of times they're the same. What if I made it x squared plus 1? Can you point what's going to happen to my original parabola if I draw x squared plus 1? So it's going to move up 1. How many x-intercepts does that one have? 0.
If you do minus 1, then it has 2 x-intercepts.
That's right. So you could do x squared minus 1. And you'll find the 2 that we expect. So you could get 2, same as the degree. You could get 1 if it happens to just barely touch the x-axis, or you could get none, but at most n. So that x squared thing will never have 3 x-intercepts. Never, ever, ever. Could have 2, could have 1, could have 0. Okay, number 8, we'll go to Joe. Okay, you don't need to read it. So there is a polynomial. What's the degree? Is degree 5. How many turning points do you expect? At most 4. How many x-intercepts do you expect? At most 5. But this is quite a complicated function, and the graph is going to be quite complicated. But there's going to be some very easy information that we're going to get from that whole thing. Just trying to think about graphing it. So I made this little sketchpad thing up. There is the complicated graph of the equation that we were just looking at. First of all, how many x-intercepts? You see 5? 1, 2, 3, 4, 5. Yes, as expected. How many turning points? 1 at the top, 2, 3, 4, just barely at the bottom there, as expected. Here's what I'm interested in. I'm interested in ignoring everything except for the leading term. Remember we used that vocabulary phrase, leading term? 0.005 x to the 5th. That is the leading term. Graphing x to the 5th, it's not hard. X to the 5th looks an awful lot like x cubed. Can you guys point in the air and draw y equals x cubed? Do you know that one yet? It's going to be hard to make with your arms, but if you kind of draw it in the air, x cubed starts at the bottom left, goes up, kind of flattens out at the origin, and then keeps going up in the top right. X to the 5th looks, well, just like that. Starts in the bottom left, goes up, flat at the origin, and keeps going up to the top right. Would you say that the green, which is just the 0.05 x to the 5th, and the blue, which is the whole equation, look similar or quite different? I would say they look quite different. But if we zoom out, would you say that the green and the blue look similar or quite different? They look quite similar. So when we're zoomed in, when we're looking close, when we're looking near the middle of the graph, they look really different. I would say they have like nothing to do with each other. But if you take a zoomed out perspective, then all of those hills and valleys, those things that seemed extreme, like it went really high and really low, if you zoom out, well, the blue one just kind of flattened, right? I mean, like I could barely even tell that the blue is doing this crazy up, down thing. Sarah, can we put that away? So the point is this. If you only look at the leading term, which is this 0.005 x to the fifth, and you know what the graph of the leading term looks like, which is generally pretty easy. It looks like x cubed, it's the green. Then you can tell me what the blue is going to look like at the far right and at the far left if I take this zoomed out perspective, okay? So the point of all this is that if you know what x to the fifth looks like, up and to the right and down and to the left, then you can tell me that this whole long complicated thing in blue looks the same if I zoom out far enough, all right? Okay, so let's go to Katrina for number, this according business. Okay, so P of x is the blue. If x is going to infinity, we are walking to the right. That's where x is infinity. It's way out here. What happens to the y values if you're on the blue? If you trace points that are on the blue, what's happening to the y values? They go up to infinity, yes? If x goes to infinity, which is to the right, y goes to infinity, which is up. So that's what we're saying in here. As x goes to infinity, so does y. The next one says as x goes to minus infinity. Again, looking at the blue, x goes to minus infinity. Can you point which way are we saying when we say x is minus infinity? X going to minus infinity is to the left forever. What happens to the y values on the blue? Can you point? They go down forever. So what are the y values going to? Also negative infinity. So that goes here. Now I think this is the first time we've seen this kind of notation with the arrows, but is it self-explanatory? As x does something, y also does something. That's all that that says. Okay, turns out that x cubed, you guys told me, looks kind of like this, and x to the fifth also looks like that, and x to the seventh also looks like that. They all kind of look like that when they're odd. So I've got this dot, dot, dot stuff happening here in the middle, and that's our way of saying if you zoomed in, I can't tell you anything. But at the moment, if you zoom out, I can tell you that anytime you're looking at an x cubed type thing, or any odd power, if the leading coefficient is positive, it goes down and left, up and right, just like x cubed does. What if the leading coefficient is negative? What does negative x cubed do? Doesn't do the opposite, flip it over the x-axis. So negative x cubed, instead of starting here, it would actually start up there. And instead of ending here, it would end down there. So if you are odd, you just need to think of, are you a positive, which makes you like positive x cubed, this kind of thing? Or are you negative x cubed, this kind of thing? So, what about the slope? Yeah, that's a good way to think of it. If the slope of a line is positive, it goes like that, right? Which if you just look at the end behavior, that's what we're doing. And if you have a negative slope, it's like that. That's good. Thank you, Joe. In the next picture, if you have something that's even, then you're thinking x squared. X squared normally goes up on both sides, right? Far left it goes up, far right it goes up. That's these two pieces here. Can't tell you what's happening in the middle. For x to the fourth and x to the sixth, any even thing could do crazy stuff in the middle, but zoom out enough, it goes up on both sides. But if you're looking at something like negative x squared, now what does it do on both sides? It goes down on both sides. That's this piece and that piece. Understand what we're looking at here in these four pictures? Here's what I'd like you to be able to do with them, is fill in the blanks. I've given you two polynomials, f and g. I want to know as x goes to infinity, what does y do? And as x goes to minus infinity, what does y do? Check with your neighbors as you fill in those 4 blanks. Okay, let's come on back together. For part A, even or odd? For part A, what is it? Even or odd degree? Even at 8. Is it a positive or a negative coefficient? Positive. So I'm thinking of like a positive x squared, which I know goes up on both sides. Up on both sides means infinity. For the next example, even or odd degree? Odd, that's 27. Positive or negative coefficient? It's a negative coefficient. Normally my x cubes do like this. I always think of like John Travolta in Staying Alive whenever I do this part. So normally x cubed is this, but this is negative, so it's that. So if x goes to, what's the first one? If x goes to infinity, what are we doing? We're going down to negative infinity. And if x goes to minus infinity, that's that way. What are we doing? Up to positive infinity. Okay. So I don't know how this is going to go. I haven't tried this before and wasn't planning on it, but let's give this a shot. I just typed in, let me make this a little bit bigger for you. I typed in the very first function, the 0.3x cubed and all that stuff. Let's change the font. Okay, so ignore the bottom one, but the top one is the first function, 0.3x cubed, x to the 8th and all that stuff. So here is my picture. There it is. Not very satisfying. What did you guys say as we went x to infinity? What was happening? Y goes to infinity. This was the top one. And if x goes to minus infinity, then it also went to infinity. So ultimately, I need something that goes up and left and up and right. That's what I'm looking for. This doesn't look like either of those. Well, maybe up and left. It's hard to tell. What that means is that I'm not looking at a good picture in terms of this end behavior stuff. So first thing I'm going to do is I'm going to bring this guy in and see, oh, all right, so now things are really starting to look different. Okay, what do you guys think? Up and left, does that make sense? Yes? Down and right, is that what you predicted? What did you predict? You predicted up and right. This is the first one. You predicted both sides would go up. It's not. What's wrong? I need to keep zooming out. Like, then there's no way. I'm already at 500. I mean, it feels like that's reasonable. I don't know. I think you guys are lying to me. It sure feels like it wants to go down and right. Look, we're at, what is that? 300? Is that 3 million? I'm at 3 million. That sure feels like, are we getting there? This was a very persistent thing trying to get down to the bottom, but I think we are getting there. There it is. There's the turning point. 10 to the 16, is that like billion? What is that? 10 to the 16 is on the order of 10 quadrillion. It's a lot. So 1 followed by 16 zeros. So if we did not know what to expect beforehand, I sure feel like we would not have had patience to keep looking, right? We would have believed the first graph that we saw, which seemed like it was going down and to the right. It was very persistent going down and to the right. But we knew with not a lot of work, all you had to do was grab the power that was even, and the leading coefficient is positive. I know this is going up on both sides. Just means you got to be patient to find it, okay? All right, so all this said, the calculator and the computer are going to be better at graphing than we will ever be. But we need to understand what we're looking for so that we're not tricked, right? It was really easy to fall into that trap. Okay, let's take a look at the other one. I will go back to the standard axes and see what it looks like here. Okay, so, all right, so this is the bottom one now. This is the x to the 27. What are we expecting at the far left? Up or down? At the far left, that was x is minus infinity, we expected up. And on the right, we expect down. I don't even know like which way we're headed on the curve, like if it's headed up or down at that point. So let's see if we can start grabbing and bring things in. So like you can start, finally, you see it curving. All right, there's the top right there. It turns around there. How's that look? What did you predict? To the left, what was it supposed to do? It's supposed to go up. To the right, what is it supposed to do? It's supposed to go down. It is. Okay. What's that? Yeah, I think that the other one was a challenge because x to the 8th had a 0.3 in front of it, and the x to the 7th had a 56. And the x to the 7th was winning for a long time because 56 dwarfs 0.3. But eventually we found it. Here, x to the 27th just has to overcome, x to the 19th. No problem. So there it is. Okay, let's come back here. Number 11, who's our reader now? Brian? Okay, give that a shot in your groups. Okay, let's take a poll. Raise your hand if you think this is always true. Raise your hand if you think this is sometimes true. Raise your hand if you think this is never true. Okay, so let's first make it clear what we're talking about. When we say end behavior or end point behavior, we are saying x goes to minus infinity and x goes to plus infinity. We just want to know, what is the graph doing when you go forever left or forever right? Does it have the same behavior, meaning both up or both down? That's what this is asking, okay? If I've translated for you like that, does that change our answers? If it's even, what can you say? Both up or both down, always the same. So this is always true. If you are odd degree, then on the one side you go up and the other you go down, right? If you're odd degree, one side goes up, one side goes down. So the end behavior for odd would always be different. Always have different end behavior. Okay, how about we go to 12? Michael. Okay, so let's look at this equation. I want to know solutions to it. I want you to see that foiling and distributing is not a good idea. No. But it's factored, and factored equal to 0 is the goal of almost every equation you're trying to solve. So what you can do is split it up and say each one of these things in parentheses has to equal 0, right? Or one of them has to equal 0. So what value of x makes this thing equal to 0? 5. Can you guys write down the other 4 solutions to that equation? Everybody's okay solving that equation? Michael? Very good question. Really what we're doing is we're setting each of the factors equal to 0. So we technically have 6 equations, all of them equal to 0. 5 of them are easy to solve and you get the answers I wrote in blue. The last one, many zeros. For what values of x is that true? None. So it doesn't have any solutions. So I ignore it, but I'm glad you asked me why did we ignore it? Like we should think about it for a moment. And once we're comfortable, just say, oh, we ignore it. It never contributes anything. Good question. Okay, part B. Tyler. No, you don't need to. So I want the zeros of that, and Tyler just read us the definition. A 0 is a value of x It's a value of x that makes the function equal to 0. So for example, so what you're trying to do is figure out when this is equal to 0. So what are the zeros of this function? 5, 10, 2, -3, -7, right? We haven't done anything, but I just want to highlight that word 0. It means you take your function and you make it equal 0 and you solve for x. Now we're actually going to do something in C. Let's go to Taylor. Okay, so I've graphed P for you right there. Go ahead and grab the x-intercepts, write them all down for me. What do we notice? What are the x-intercepts? They're the same as the zeros, right? It's exactly the same numbers. Does that make sense? Is this a coincidence? How do you find x-intercepts? You set y equal to 0, right? Isn't that exactly what we did right there? We set y equal to 0, the whole thing equal to 0. So of course, the zeros that we find by solving that equation are going to be the same. They're going to show up as x-intercepts because that's how you find x-intercepts. You let y equal 0. Okay, so I'm hoping it's obvious that the x-intercepts match up with the zeros, but it's a little bit of vocabulary. We're going to see it again real soon, but I just want it to be clear, you know, like it feels like we're not doing anything, but that's an important thing that just happened there, that x-intercepts are exactly the same as zeros. Okay, we'll go to D. Sarah? See what you did there, the equation? Okay, how many extrema, that is how many turning points does it have? We count them, we see 4, right? Top, bottom, top, bottom. Does 4 agree with what we had said? Number of turning points is probably 1 less than the degree. Number of x-intercepts is probably equal to the degree, was it? Number of x-intercepts was 5, equal to the degree. I say it's equal to the degree. Is it clear to you that the degree is 5? How would you verify that the degree is 5? In theory, that's when you got to multiply them all out, right? But we don't need to because we know that the highest power you're going to get is when you grab that x times that x times that times that times that. I suppose it'll have a 0.005 in front of it. It'll be x to the 5th, right? Okay. All right, let's go to number 1. This is our group thing, but let's read it together and make sure we're on board before we go to town. Andy? Okay, I'm pretty sure you guys have seen this problem before. Have we seen this kind of thing before? I think we've seen it this semester in some homework thing. So you take your 8.5 piece of paper, 8.5 by 11. You're going to cut out congruent squares. That just means equal squares from the 4 corners. I've called them an X because I don't know how big I want to cut out the squares by. But you just cut out the same square from all 4 sides, and then you fold up the things that are still there. And you should get that box over there. And do you guys see that this blue height right here it's the same as the X in that picture? That's how tall the thing will be. Okay, so the group activity is here, and there's a follow-up problem on the back, and there are, I think, answers too. But let's see if we can work our way through this.